Final derby, right? Anyone remember um, what topic that related to? It related to kinetics of rigid bodies. Okay, rigid body kinetics. So for kinetics of particles, you use Newton's second law. For kinetics of rigid bodies, you use Newton's second law and the rotational version of Newton's second law. And that related to a lot of rolling things and objects rotating around like pin joints and hinges and stuff. So now we're getting into what I think is, well, one of the two most interesting topics to me in this dynamics class, kinetics of linkages. So the next topic is, well, since the rigid body stuff we've been doing is only 2D, remember 3D gets extra complicated, and we're probably not going to get to any of those. These linkages also have to be 2D, so 2D linkages. And for the people who took statics, so a linkage is just a collection of bodies connected by joints. And so if you apply forces to it, it goes in a funny way. And actually, like the human body is a linkage. You have a bunch of rigid bodies connected by joints. And if your muscles apply forces here, or if some external force is applied to you, the motion of the body is this complicated set of reactions to the joint forces and the external forces. One way you can think of a linkage is like in statics, we talked about structures. So a structure is something that it's fixed in place, you apply loads to it, and it doesn't move, but the reaction loads, are developed. If you took one member away from a structure, now it would be something where it couldn't support the load without moving. And if you applied a force to it, it would, go down to the floor or do this. So, well, we didn't have linkages. We only had structures because the only stuff we calculated in statics were collections of bodies that would stay still when you applied forces. So a linkage is a collection of rigid bodies connected by joints. In this class, they're almost always going to be pin joints. And this is just the basis of so many useful things that you calculate in dynamics. The basis of machines, biomechanics is all based on this, at least orthopedic biomechanics, where you're talking about muscle and bone forces. Robotics is all based on this. So this gets into a lot of really interesting topics, and I think it's fair to say that the most likely thing that you'll use dynamics calculations for in your future classes is linkages. So let's think of this example. We're going to do this problem, but I just want to first use this to introduce the idea. So let's say that we have a rigid body that's connected to the wall at a pin joint here. And then it's connected by a pin joint to another body like that. And let's say that this is a pin and slot joint. Bless you. Let's say these two angles are 70 degrees. The lengths of the two members are each 3 meters. And let's say that there's a 600 Newton force applied to the pin. Well, if this was a piece of an engine or a part of a machine or something, and this was something, you know, like a company was making or you were using in research or something, there's a lot of things you might want to know. You might want to know what reaction forces are happening at those joints. You might want to know what the acceleration of this pin in the slot is. You know, maybe that's being used to apply some kind of force to something else. And I guess, so let's say, well, I'm going to calculate all of those. So what are the external loads on each member? And what's the acceleration of that point? Well, let's call it P. And it looks like I'm neglecting the masses of those members. Nope. Each one of those has a mass. You don't have to, but I just wanted to match what I have here. Oh, actually, now that I think about it, yeah, if you're doing dynamics, yeah, there need to be masses on those members. In statics, there don't have to be because it only comes up as the weight force. Mhm. Mhm. Oh, yeah. If you're isolating a rigid body, you need to know its mass. So the mass of each member is 10 kilograms. Okay, so I'm going to give a set of steps that you can sort of think through for general linkages. It looks like only 2 steps, but that's pretty deceptive because the first step is for each member, do the rigid body analysis, which involves those 6 steps from before, you know? So it's like I'm trying to trick you. So steps for general linkage problems. So first, for each member, go through the steps of rigid body kinetics. Yes. How do you do rigid body kinetics when you have 2 members that depend on each other? Well, you still, so I'll go through this example, but you still think about it just the same way. You know, this one has a fixed point, so we're gonna, so the about point for, let's number these. You just basically go through this rigid body analysis. You don't have, yeah, I mean, you're going to do them one after the other, and you're just going to come up with a system. You calculate the moment of inertia around that about point. Then free body diagram, come up with the rho and the force and the moments. Since this has a fixed point, we skip Newton's second law and go right to rotational Newton's second law. And we come up with one equation from rotational Newton's second law, you know, the z component of Rn2L. And we have too many variables, just like remember in statics when you would isolate one body, you know, you isolate the first body of too many variables for the number of equations. So we'll just set that one equation aside. And then we'll go to this one. Does that one have a fixed point? No, every point on there can move. So for this one, the about point is going to be the center of mass. Calculate the moment of inertia about the center of mass. Free body diagram, rho, force, moment. And then for this one, since there's no fixed point, you have two equations for Newton's second law, a third equation for Rn2L. And so now you have a total of 4 equations. In statics, at that point, you're done, if you remember. Okay. In dynamics, with a linkage, you're not done. You have 4 equations, but you have more variables than that. And the way that you come up with, which means you need more equations, right? And the equations that you come up with are geometric constraint equations that enforce the way that these joints have to act. Like, for example, we know that this point, at this point, the acceleration according to member 1 and the acceleration according to member 2, they have to match. That's what it means for those to be pinned together. Okay, so we can use the watermelon equation to calculate that acceleration according to this, and set them equal. And this, since it can only move along this slot, it can't accelerate perpendicular to the slot, only parallel. And that gives us another constraint equation. And so when you add up all the Newton's laws, take all those equations and then add to that system all those constraint equations, you have a system. In this case, it's going to be 7 equations for 7 variables, and you can finally solve it. That's right. Okay, so let me write this all down. So the first step is for each member, go through the steps of rigid body kinetics. If the body has a fixed point, we're going to get one equation from this. Rotational Newton's second law gives one equation. Remember, we're doing this in 2D. And if the body has no fixed point, Newton's second law gives 2 equations. Rotational Newton's second law gives 1 equation. And that's a total of 3 equations. Again, that's in 2D. That's all we're doing is 2D problems. Yes? No, because it adds more variables too. I'll show you how that works, but that doesn't help. One thing to remember is to be sure to use Newton's third law to write these equations with as few variables as possible. So what I mean by that is, in this example, when we're isolating member 1, think of a free body diagram of member 1. There's going to be a force on 1 by 2 at that joint. When we isolate member 2, there's going to be a force on 2 by 1. When we describe them like that, that's two different vector variables. But Newton's third law says they're equal and opposite. And so you have to make sure you're not writing in your equations F12 and F21. It should be F12 and negative F1. Okay, that's step 1. That's a big step, though. That's the step that takes forever. And then step 2, count the equations and variables. The difference is the number of constraint equations you need. Yes. And so the way to do that is at each joint that's not fixed, you're going to use two equations. First, the watermelon equation. So the acceleration is equal to, actually, let me write this in a different order. So there are two things that are going to come into this. First, relative motion often comes into it like this. The acceleration of the point P, whatever point you care about, relative to the ground, is equal to the acceleration of the point P relative to the center of mass, plus the acceleration of the center of mass relative to the ground. And or, second equation we'll use is the watermelon equation that says the acceleration of P relative to the center of mass is alpha cross R plus omega cross R. And you can think your way through this. You know, it won't make a ton of sense at first, but you can make sense out of this with stuff that we know so far. It just, you know, and I'll try to sort of talk us through it as we go. But this R is a vector to the point P from the center of mass. And then alpha and omega are just the alpha and omega for that rigid body. One thing that can be a little tricky, is what do you do when something happens at a joint? This is going to make more sense to the people who've had statics because we had to do this a lot in statics. But like, for example, in the example problem that I drew, that 600 Newton force is applied at that pin, and that pin touches both of those two bodies. So where do we put that force? Well, what you need is a system so that whatever's happening at that joint, whatever's happening directly to that joint, you either treat it as it's happening to 1, or you treat it like it's happening to 2. If you treat it like it's happening to 1, and you also treat it like it's happening to 2, that's the equivalent of a 1200 Newton force happening there. Okay, and so I'd recommend you come up with a system, and any system you want works, but the one I'm going to use is, since I'm always going to number these members, I'm just going to assume that the pin connecting these things, the joint itself, is part of the lower numbered member. Okay, just like in statics, that's what I did. That's no better than any other system, but it's just the one I'm going to use. So you might want to do it that way. But if you're the kind of person that, then that's definitely, like Mike probably is this kind of person. He's gonna and be like, oh well, that's the last thing I'm going to do. Then I'm going to make it part of the highest numbered member. That works fine too. It just makes more work for me. And now Mike's like, oh, then I'm definitely going to do it. Okay, so notice loads at the joint should be applied to one member or the other. Yeah, you can treat it as a yeah. Mm-hmm. Yes, you're exactly right. If you knew all the properties of the actual physical pin, you could just treat it as a rigid body. We're never going to know that. I mean, in these kind of problems, and you'd get, well, if you know those values, it wouldn't take that horribly much longer. It would add to the number of equations and variables a little bit. But since we won't ever know them, do it this way. So the loads at the joint should be applied to one member only. I'll always apply it to the lowest numbered member. Okay, well, let's go through this example. So the example I'm going to do is the linkage problem above. And we have 25 minutes. We're not going to get this done in class today. You know, these just take a long time. So the first step in these linkage problems is to come up with Newton's laws for every member. So I'm going to start with member 1. And I'm going to go through the rigid body kinetic steps. So member 1, does it have a fixed point? Yes. Let me label these. So I'll call this A, B, well, I guess that's already P. So the fixed point is at A, right? A is fixed. So the about point is A. Step 2 for rigid body kinetics is to calculate the moment of inertia about A. The moment of inertia about A, remember, is equal to the moment of inertia about the center of mass plus md squared. This is a slender rod. We're not given a thickness. So this is just 1/12 times the mass of the member times the length squared. The length was 3 meters. And now the parallel axis theorem part, the mass is 10. What's the distance between the center of mass and the fixed point, the about point? 1.5. Any questions about that? Yeah. Yeah. So this is A. And so that distance D is the distance from the center of mass to the about point. That's half of the length of it, so 1.5. And I think I have that. That comes out to 30 kilogram meters squared. What's step 3? Yep, free body diagram. Is that what you said? I'm going to see. Okay, good. I like when people just like go like mumble something and then yeah. But then if like you always say dumb stuff and then you mumble, I'm going to assume you're wrong. So it sort of cuts both ways, you know. Yeah, right. No, not right. Okay, so free body diagram of member 1. Okay, so what forces are applied? Yep. Let me put the weight first. So it's a mass of 10. So the weight is acting at the center of mass, 98.1. And then, yeah, there's a contact force applied by the pin joint on the wall. So I'll call that R. All right. And then down here where the two bodies touch, there are two things going on. First, there's the 600 Newton force that's applied to the pin. But what I said was I'm always going to assume the pin is part of the lowest numbered member. We have 600 newtons like this. And then second, we have the contact force between those members. That's the force on 1 by 2. Bless you. Any questions about that? Step 4. I'm going to calculate rho, force, moment. The about point is here. That's already been chosen. So what's the rho vector for the force RA? 0. The force vector is RA, x and y components. And so there's no moment. What's the rho vector for the force 98.1? The vector is this. We want the vector from RA to the point where the force is applied. So you can think of that as 1.5 times cosine and sine of 200 degrees. And that comes out to be 1.41, 0.51. force is 0, negative 98.1. What? Yes. Yes, thank you. And then that cross product is positive 138.3. Does it make sense that that moment should be positive? Our about point is this. If you apply a downward force over here, that's going to make it rotate counterclockwise around that point. So yeah, that makes sense. And then the next one is the force F12. Rho vector there is 2 times this, so negative 2.82. And this is actually negative 1.03. The force vector is F12x, F12y. And the cross product is negative 2.82 F12y plus 1.03 F12x. And then one more force. It's acting at the same point, so the rho vector is still negative 2.82, negative 1.03. The force vector is positive 600, 0. And so the cross product is 18. Because this was rounded off. Okay. You know, that's, you get 1.03 if you use 3 times cosine and sine. Yeah, right. And then does it make sense that that's a positive moment caused by that force? Yeah, if you took a little mallet and tapped this here and it was pinned here, it would make it rotate counterclockwise. So that's positive. Okay, now here is something that's going to happen a lot. At this fixed point, all right, well, let's think about how many variables we're going to get from this. Okay, how many variables are we going to get from analyzing the first line? 2, 4, and then, well, and actually, let's just think about the force variables. Okay, don't worry about the acceleration variables for now. How many force variables are we going to have? Well, 4, right? 2 for RA, 2 for F12. Well, it turns out that we're only going to have 2 force variables in this equation. And the reason is, since this has a fixed point, we're not going to use Newton's second law. Okay? And so we're not going to add up this row. We're only going to add up this row. And so in the rotational equation, that reaction force with the wall doesn't show up. Okay? And so adding up your variables, adding up your equations is a big part of this. And you have to be sure that you don't add up your variables based on this table. You only add them up once you get to the equations. You know, there could be 100 variables in this table. The only ones that matter to us are the ones that end up in Newton's laws. Okay. So, step 5. Do we need Newton's second law? Right. No Newton's second law. So step 6, the rotational equation says 138.3 plus 1.03 F12x minus 2.82 F12y plus 618 is equal to the moment of inertia that we calculated, 30, times the angular acceleration of body 1. And I'll rearrange that. Let's see. So that is 140, 56.3, 756.3 over here. So we have 1.03 F12X minus 2.82 F12Y minus 30 alpha 1 is equal to 756.3 negative. And I'll call this equation star. That's the first equation in our big system. So we have 3 variables. That's F12, the vector, those components, and then alpha 1. Any questions about that first body? So we have one equation. That means we can't solve anything yet. We'll just set this equation aside and we'll come back. And now we'll go to member 2. Does member 2 have a fixed point? Nope. Every point on member 2 can move. So since there's no fixed point, the about point is the center of mass. Yeah, the only thing we care about in step 1 is, are there any points that have no velocity and no acceleration? That's fixed. So the about point is the center of mass. And now the moment of inertia, we're going to calculate that about the center of mass. So I COM is equal to 1/12 times the mass times the length squared. And that's 90/12ths, which is probably something sort of simple. 30/4ths, 7.5. Yes. Take that, doubters. 7.5 kilogram meter squared. Step 3 is a free body diagram. What loads are acting? First, there's the weight, 98.1. Over at the connection between the two bodies, what's happening there? Yeah, so there's the force on 2 by 1, and I'm going to write that as negative F12. It doesn't matter when you make that switch, you just have to do it before your final system of equations. So negative F12. What about the 600 Newton force? That's not there because that's acting on the pin, and we said the pin is part of member 1. And now the pin and slot joint, you got to go back into your memory banks for this one. What kind of loads are applied by the pin and slot joint here? That's right. It allows this thing to translate freely this way, so there's no force parallel to the slot, but there is a force perpendicular to it. So I'll call that the scalar RC. And we know it's, well, we know it's either pointed this way or this way. It doesn't matter which way we choose. I think since this is sort of a simple problem and the only external force is pushing it that way, it's pretty reasonable to guess that this force is going to be that way. But if that comes out negative, that's no problem. And now we need the row vector, the force vector, and the moment. About point is the center. So I'm going to do the weight first. What's the row vector for the weight? 0. Force vector is 0, negative 98.1. Cross product is 0. What's the row vector for negative F12? Who knows? I think that's negative 1.41, positive 0.51. That's just a cosine and sine thing. What? 160. Yep. The force is negative F12x, negative F12y. And the cross product is 1.41 F12y plus 0.51 F12x. And then the row vector for RC is positive 1.41, negative 0.51. The force vector, that's in the negative x direction. So the force vector is negative RC 0. And so the cross product is negative 0.51 RC. Any questions about that one? All right, so 5 is Newton's second law. Do we need that in this case? Yes, because there's no fixed point. So 0, negative 98.1 plus negative F12x, negative F12y plus negative RC 0 is equal to the mass times the acceleration of the center of mass, right? That's Newton's second law talks about the acceleration of the center of mass. So I'm going to call this, well, I guess I'll, at least for this first example, I'll call this the acceleration of the center of mass, body 2, x and y. That's a big and then rotational Newton's second law. Well, actually, let me write out these equations. So that says that equation double star, our second important equation, says negative F12x, negative RC, minus 10A COM2 x component is equal to 0. And triple star says negative F12y minus 10A center of mass of 2 y component is equal to positive 98.1. Step 6 is the rotational equation. And that says 1.41 F1, well, I guess I'll change the order. So 0.51 F12X plus 1.41 F12Y minus 0.51 RC is equal to the moment of inertia about the center of mass, 7.5, times alpha 2, the angular acceleration of body 2. And this gives the fourth important equation. I'll call it 4 star. 0.51 F12X plus 1.41 F12Y minus 0.51 RC minus 7.5 alpha 2 is equal to 0. Now we're done with Newton's laws. So after Newton's laws, we have 4 equations. And how many variables? From body 1, we had F12 and alpha 1. From body 2, now we've also added a variable RC, an acceleration vector, COM2, and the only other one is alpha 2. So that's 2, 4, 5, 6, 7 variables. That's right. Okay, so that tells us that after Newton's second law, we need 3 constraint equations. We're going to get those from the joints, and we'll do that on Wednesday. Any questions? Okay.